Okay, then let's continue. So there are at least two things about excursion sets that are fairly intuitive and straightforward and not surprising, but will be used a lot in also the formalized approach to excursion sets to then allocate probabilities of, for example, certain aspects of the excursion set exceeding a certain value u that I want to discuss next. And the first thing is that I cannot draw straight lines. And the next thing is that the excursion sets, irrespective, if you want, of realizations, let's say like this, well, that's almost no function anymore. Like this, maybe. Excursion sets, if you increase the threshold, they show so the U, the level, they show a predicted behavior. So that's fairly obvious, but nevertheless used quite a lot. So, for example, if you use first this threshold, then you see that the excursion set now drawn here in the domain of the field, which is in this case just a process, is geometrically somewhat complex because it consists of one interval here, then what will be called a hole, and another interval here. Yeah. That's relatively easy to see. Now, the question is what happens if one increases the threshold. So we are now looking at this process that we increase U, and then what will happen happens regardless of a specific realization. So maybe I put another one here. So that's another one. If you increase the U value, the level, so the complexity of the excursion set decreases. So, for example, if we're still looking for the black one, then this one, so this part here would now not be in the excursion set anymore. So the excursion set gets a lot simpler. Now the whole line is gone. For the other realization, we see that the excursion set gets really, really small. So this might only comprise the point here, which is the point in which this realization takes its maximum. And then if we increase the threshold even further, or the level even further, then this also happens for the first realization. So now it gets smaller. So the first thing is that as you increase the threshold, the number of connected components, if you want, of the excursion sets gets smaller and smaller and reduces to 1. So here only one thing, because there will always be one largest peak, and if you increase the threshold further and further, only this largest peak and the values in the domain will still be part of the excursion set. And then if you get really, really close with your threshold to the maximum, then if you are exactly at the value of the maximum, then the excursion set only contains a single point. So then it only contains the point where the realization assumes its maximum. And then if you go even further with your threshold, then the excursion set is empty. So that's fairly easy. So the first thing that you need to get a feeling for is that when you think of realizations of random fields, think that each of these realizations, in this realization, there will be one largest peak, yeah? Like Mount Everest. Yeah? So there's one largest peak. And if you now increase the threshold even more, then you will, or the level, you will threshold out everything that is at one point smaller than Mount Everest, and only include the excursion set that corresponds to this largest peak. So it will get the excursion sets will get smaller. There will only be one connected component. Then, if you're actually at the peak, then the excursion set only contains one point, and if you're above the peak with your level, it's empty. It's fairly straightforward. Questions about this? It will be used nevertheless a lot, and one needs to think about what that means. The other thing that we then also want to follow today already in a more mathematical fashion is that the excursion set also depends on what is called or referred to as smoothness. And this is not smoothness in some kind of a real analysis thing where I think it means that the second derivative of a function is also differentiable, I think, or at least exists. That's not the smoothness we mean here. The smoothness we mean here is really an intuitive smoothness in the sense that this is smooth and this is not smooth. Yeah? Again here, if you think about the excursion sets, for example, for this level, there is something kind of predictable about these excursion sets. If something is smooth, then what will likely happen is that the excursion set comprises few but maybe a little bit larger components. If the random field is rather rough, that's the term that is used for non-smooth, so it's kind of the continuum from rough to smooth, then the excursion set contains smaller but more unconnected components. Yeah? I think that's fairly intuitive. I can't think of a real good example. So smooth is something like the Shire in Lord of the Rings. That's smooth. Or in the Midlands in the UK, these, what are they called? Rolling hills. That's smooth. And then, I don't know, the Dolomites, are they rough? I don't know what is rough in the real world. Life is rough, but that's more a general thing. So smooth random fields have excursion sets rather comprising few and larger components, and rough fields have more components. So the same, of course, applies in 2D and even more in 3D. And I want to show you that briefly now. So what I just discussed in terms of these intuitions about excursion sets, that's also visualized here. So the first thing shows the most important thing, maybe, that if you have the same random field, if you have the same random field but draw multiple realizations of this random field, the excursion set differs. So here, this is a realization from a Gaussian random field with a Gaussian covariance function with a specific smoothness, not smoothness, with a specific L parameter and a specific V parameter for the covariance function. Of course, the expectation function is 0, and it's scaled to -4 to 4, as you can see. And this is then below the excursion set for a U level of 2. So everything that is larger than larger or equal to 2 is included in the excursion set. The excursion set is here marked in white. We always remember that the excursion set is in the search space. So in this case, it's the excursion set is a subset of R2, or more specifically the search space, which is here the 1 by 1 unit square. So here you see the things that are larger than 2. Makes kind of sense. This is another realization of the same random field with the same threshold, but the excursion set, because the realization looks different, the excursion set also looks different. And the same here and the same here. Yeah, so these are realizations of excursion sets, and we would be interested in studying the probabilistic properties of the excursion sets. So the expectations and distributions of aspects of this. So the next figure here, B, shows what happens if you increase the level. So here I have one realization. Of course, you should generalize this, that the same kind of thing happens for multiple realization, but here I'm doing it in one realization because then it's easier to see. Here I have a number of thresholds, -0.5, 0, and 2, which are here shown as planes. So in general, I don't do these 3D plots, but here I thought I could do one. I didn't do a movie. As you see, the excursion set follows a predictable path. So first, you have in the excursion set quite a lot of connected regions, but also holes. And then holes tend to disappear because you break up essentially the holes. And then if you go larger and larger, the number of components of the excursion sets decrease. Actually, I was trying to get a realization where I really only have one component. Here I still have this and this. But then doing the whole figure takes like half an hour or so because it's fairly high resolution. So then I got a little bit tired and didn't start it again, and hoping for just a single component here. But this is where if you would increase further, I don't know which component is the largest. Maybe it's actually this one here. Only this would show up. Straightforward. And finally, the thing with the smoothness. So here, Gaussian random field with Gaussian covariance function with a fairly small L parameter, which then, of course, gets less blobby. And the excursion set has many unconnected components. And here, a smoother random field and one realization where you have one component, and these are both done at the same threshold of 1. And you have to interpolate this to the 3D case in your head, because I can't be bothered to try to visualize that. But of course, you can always see this 2D realization as a cut through a 3D realization, if that helps. Good. Questions about this? No. Good. So what we ended up with essentially now is the question, okay, we want to describe the probabilistic features of excursion sets. So maybe just to give you a glimpse of why this is interesting in terms of fMRI is of course because if you now think you observed one t-value, so you have your t-map, so you are suddenly discrete here again. So you have a t-map here, and these are the points where you obtain t-values, and then let's say you have a t-value obtained here, which is of this size. So that's your t-value here. Then, of course, you would like to know what is the probability that t is larger than a level u. Think of your t distribution and the notion of a p-value. What is the probability that t is larger than u? And just by looking at this, from what I've drawn here, I would say, well, that depends of what kind of random field governs this distribution of t. If the field is rather smooth, then I would say the probability that t is larger than u is actually not that high. So your p-value would be quite small, so that's something significant. And if your underlying field is rather rough, I would say, well, there's a good chance that actually something is larger than the value u. So the probability is rather large, and so your p-value is large, and it's rather not significant. So this is kind of the logic that we will use at various levels. This was actually peak level inference at various levels later on, and in a quantitative manner, so that you don't only use this intuition, but also get a number, which you then should always interpret, of course, in light of your intuition. So what this is demonstrating is that smoothness matters. And so smoothness matters for a random field theory-based p-value correction. And if you want to evaluate p-values then in a quantitative manner, then you also need to quantify smoothness. And that's now the next thing, to look into how random field theory quantifies smoothness of random fields. Someone thirsty today. Measuring smoothness of a random field, that's the next thing. And this is where we actually get really into the fMRI literature on this. You have the references. I didn't put them into that yet, into the folder, but you have them in your script. It says what the references are. And if you think what I'm presenting here is kind of complex and confusing, look into the primary literature, and then you will appreciate finally what I'm doing here. Because already this measuring of smoothness of random fields in the fMRI literature it's not that you find kind of like in 1990, before this whole started, they said, okay, this is how we measure smoothness. Now let's, for the next 28 years, measure smoothness this way, because we want to have a consistent and coherent story about the whole thing, and so that everybody like who's new in the field can just read the old paper, and then everything is fine, and it's a walk in the park. This is not really what happened. For smoothness, it's actually better than for other things, but with smoothness, it also starts of getting a little bit funky, the whole thing in the fMRI literature. So I'm trying to add a little bit to the fMRI literature with this, and trying to make it a little bit, more, a little bit cleaner maybe. Taking into account, of course, also things that in the early 90s were not that deep in the literature than they were in the late 2000s. So, having said that, I now say that the principal measure used to quantify smoothness in random field theory-based p-value correction is the following. This is a sigma, so it's the same thing as this, but it's called it's a sigma variant, and I use it here as a symbol for smoothness, S, so smoothness. And the principal measure used in RFP, so that's equation 4.2 in your handout, is the following integral. So it's an integral over the dimensional unit square, so over the interval 0 to 1 if you are in 1D, over the square that we've just seen in 2D, so this thing, and of course a cube of side length 1 and located at the origin in 3D. It's an integral over a determinant. So the just writing up first. So these two bars here, that's the determinant. And if you know that this is a determinant, you also know that it's a single number. That is integrated over here. So determinants we did last term. We will see them again in a second. And you also, of course, know that determinants apply to matrices. So only if you have a matrix, even if you have a 1-by-1 matrix or scalar, determinants apply. And then the question is, what is this variance? Not this variance, what is this matrix? That's what I now call, after some back and forth, the variance matrix of the fields of field gradient vector. We will look more into this, what this means. So right now it's a fancy equation. The first thing that we need to define a little bit more in detail is this matrix of which we are supposed to compute the determinant, and this is given by the matrix of the covariances. This is why we looked at covariances last time, of the partial derivatives. This is why you looked into partial derivatives of the random field with respect to its, of course, with respect to the components of its domain vector. Yeah. So if you have, so the x vector, of course, depends on in which D you are. So if you are in 1D, just to make that clear, so if D equals 1, then of course, partial derivative is not that meaningful because it's just a derivative, but you can deal with that. If D equals 2, then X, of course, is two-dimensional. So then partial derivatives kick in. And if D is three-dimensional, like we have it in fMRI, then, of course, there are three partial derivatives. And now the question is, no, not the question is, the task is to understand somehow how this kind of fancy equation, I think that actually looks fancy and complex, it's almost like a physics equation, what this wants from us and how it actually captures something like smoothness. Because from just seeing this equation, it's not really clear how it captures smoothness. But one thing that one can say from the very beginning is that at least what comes out in the end is a single number. So this is something that I see already from this term, because you have something that varies over space, which is this matrix of this variance matrix of the field gradient vector that varies over space because it's dependent on x. Yeah, so there's a dependency on x, but then this for each x there's a determinant formed, so we have a single number. Then this determinant is actually taken to the power of minus 1/2, and there's a single number now for each point in the unit square, and then it's integrated, meaning averaged, if you want, over the unit square. So the dependency of this term here in the middle of this term over space is integrated out, so we end up with a single number. And then we have a single number that says how smooth a random field is, ideally. And if it was up to me, we only would have a single number. We would see that in fMRI actually we have 3 numbers, which are multiplied, which is, anyway, but we'll come to that. So if it was up to me, this would be our only measure of smoothness. There would be another way to do that. That actually would be a matrix. That's also fine, but yeah. So we need to capture smoothness, and here we capture it with a single number. And then you can say something like, this random field has a smoothness of 10, and this random field has a smoothness of 2, and this random field has a smoothness of minus 10. So the smoothest field is the one with the 10, and the least smoothest field is the one with the minus 10, and the middle smooth field is the one with the 2. Yeah. So this is what this is about. Now we have to somehow understand how this complex thing is measuring smoothness. Also, because we might want to use this, we want to evaluate the smoothness measure on real data. So, for example, you have a realization of something, and now you're supposed to calculate some p-values based on some excursion set, and somebody told you, okay, it depends on the smoothness. Then, okay, you need to know how do I measure smoothness, and once you know how you measure smoothness, then you might want to implement that. And if you only have a fancy equation that you don't understand, then it's really hard to implement it. So let's try to understand this equation. Or this definition. It's not really an equation. It's a definition. It's a measure. Not a measure in a measure theoretic sense, but a thing that you can potentially compute analytically or non-analytically based on something and then get a single number. Good. So the first thing that I always do when I see something that looks complex, I try to simplify it or apply it in a case where I hope things get simpler because the whole thing is less complex. So the first thing that I looked at to understand the smoothness thing was, okay, I said, okay, that looks complex to me. Maybe let's have a look how it looks when x is actually one-dimensional. Maybe I have a better way of getting intuition of what this thing wants from me, or maybe I can actually relate it to other things that I already know. This then is what I did. So now we're looking at the case d equals 1. Because then things, of course, simplify. We're getting rid of partial derivatives and gradients because they don't. There only exist derivatives, and we are getting rid of kind of a matrix business. So we are left with the following. this is still sigma, so I use the same letter now in the application to the one-dimensional case. Then we still are dealing with this integral. And now we are dealing, instead of with a variance matrix, we deal with just a variance. Instead of a gradient vector, we deal just with the derivative. I will say about this something in a second. And the rest, of course, remains the same. So for some people, it might look weird that I write a derivative with a point here, although we're referring to something that extends over space. So you might know that physicists love to write derivatives like this with a little dot. Usually they use this in the case when the domain of the function, so x is a function here, is time. So there's kind of this convention that this dot for the derivative means that the function is a function of time, and then the dot is the derivative of a function with respect to time. That's kind of the typical convention. And of course, in principle, our domain could be time, especially in the one-dimensional case. But we, of course, look at the whole thing from the perspective of space, where usually I would write a derivative like either this, so that's the first derivative with the prime, or like, now that's then doesn't work, dt like this, or for a general function like this. However, I found that actually in the geostatistical literature, maybe that's how it's called. So there's of course a field where people look at the statistics of things extending over space, like in what's it called, geography. I think there's earth sciences, something like that. They also do statistics. It's not only the psychologists who know statistics, also people in geography know statistics. And they have something called a variogram or semi-variogram, which is fairly closely related to this. And in this literature, there appears this dot for a spatial derivative. So, and this also you also find this then in the more mathematically advanced Jonathan Taylor literature on the whole thing. So this is why I use this dot. So don't get confused. Don't think there's suddenly a derivative with respect to time here. It's just a derivative. And now the question is a little bit more of what that means. And I think here intuition is then already quite helpful. So if you think of your general understanding of derivative of a function, so how do you, if you think, okay, somebody asked me about the derivative of this function at this point in space. How do you visualize that? Not how do you compute it. What do you think of? Lena, what do you think of? That's why I ask you what you think of. Does anyone else think of something? It's the slope of? Well, the function that is. Yeah, exactly. Yeah. So that's how the typical way to visualize things. Something like this. And now this is the slope, and now already one actually has to think a lot. Or I have to think a lot. Now, what this formula says for measuring smoothness is that we should look at this slope over the entire space that we are interested in. So let's say here we have 1. So this is 1, this is 0. We should look at these slopes over the entire space and average them after computing the variances. So that's important. But essentially, how much these slopes vary over space, this is the problem, and I think this is also a problem in the FMI literature. You have to really think about what is the variance relating to and what is this integrating over space relating to. So the variance, they relate, this is not a spatial variance, they relate to the realizations of the random process or the random field. The derivatives, they are viewed over space. You can see that, and we will get to that, how this is estimated in SPM, and this is why I'm saying this, because the derivatives, so the spatial derivatives, they are approximated or evaluated for each realization. So what does that mean? Now, if we have something really smooth, then the slopes, so if something is really, really smooth, and everything, of course, has an expectation of 0 because we're dealing with our fields of interest. Something is really, really smooth. All these slopes will be rather small, yeah, because all the slopes are very close to a straight line. Now, if you have something like this in between, then of course you have slopes like this over space. And then if we go to something that is more rough, then you, of course, your slopes get much larger, yeah. So keep in mind that this is the more vertical the slope looks, the larger the value, yeah. So maybe get a bit of this. So this derivative captures something over the entire field that shows how much this thing varies over space, yeah, and that's important. And we look at the unit square, that's also important because if something that is rough varies a lot, then it varies a lot over a specific space. We will get to that let's forget that for the moment. Let's just focus on smoothness and not so much on the relation to space for the moment. Smoothness relates to the derivative. That's one thing, and then the other thing that is in this equation is that it's a variance which also relates to the question of how much this actually differs over multiple instantiation. So if you have the same variance, let's say, if you have the same variance but increasing derivatives, then you would have a less smooth random field. Always note that this is also important in this context. The roughness is weighted positively, but then it's 1 over the roughness. Yeah, so this measures smoothness. Effectively, the derivative, they measure roughness, so they get larger for more rougher things, but then it's the inverse that is actually evaluated. Now the variance relates to variance over realizations. So if you have something, if you have the same If you have the same variance, then something that looks rougher gets a larger value. If this, in addition, varies more over realizations, then you get even more smoothness. I'm not really sure how to understand the scenario that you have larger variance, because then you would assume that sometimes you actually get something that looks smoother and something rougher, but you would call that smoother. Then it gets a little bit iffy, but the whole thing gets even more iffy if we go to higher dimensions. But the basic intuition is that with these derivatives, you can describe the spatial variability, and then you integrate this over space. So you get, if you have high values at each point in space, you get a large value in total, and then you look at how much this actually varies. You can actually view it in a different way. Maybe that's more helpful, which just occurred to me. This is actually, I think, more helpful than to think more about the variance in terms of smoothness. If you remember what we said last time for the variance, that if this is, I think, a lot more helpful. Remember the covariance between x and y, that you can compute this as the product of the expectations minus, was it minus or plus? Minus, I guess minus. I'm not good with minus and plus. In any case, you need the expectation of the product and you need the product of the expectations. Now, we are said we're dealing with expectation functions zeros all the time. So our the expectation term is 0 anyway, so we're getting rid of that. And now if we have y being x, then we also said that this, the variance of x is the covariance of x with itself. And then in the one-dimensional case, of course, this is the expectation of x squared. And this is now helpful, because essentially what this means is that you weigh, and this is something you're familiar with, you weigh positive and negative slopes equally. So you're essentially computing the absolute value. So for each slope, you're not computing the absolute value because it's squared, but if you then sum over space, positive and negative things don't cancel out. Yeah, and this is kind of, but this variance then is evaluated over multiple realizations. So the kind of variance does two things. It takes care of the variability over realizations, but also gives you this square so that you weigh positive and negative slopes equally. No? I think that makes much more sense. Okay, as I see, time is running out. So then definitely next time we should go over the higher dimensional cases. Now, there is something that I did, and I don't think I want to discuss it in the course. So I asked myself, now, if I define my random field here, so I define my x as a Gaussian random field, and I know the covariance function, then I have, in principle, specified everything that I can specify about my Gaussian random field, because I can now take samples. But I also know the analytics of this Gaussian random field. And then I ask myself, what do I get for this measure here? For a Gaussian random field that I have fully specified in 1D. And I was hoping, of course, that I recover the parameter that we already have seen to affect smoothness, which is this L parameter. So here. Here I simulated Gaussian random fields with varying L parameters, and we've seen here, and also on a slide that we looked at today with the excursion set, we've seen that if we increase this L parameter, the whole thing gets smoother. So if this measure of smoothness that we are now looking at is somehow coherent with in the whole theory, then I would assume that this measure of smoothness corresponds essentially to this L parameter. And this is what I found. That's 4.5, so that's maybe the easiest equation in the whole script. It says sigma equals L. But to derive that, that was actually some work. And I'm kind of convinced by my proof. There is one step where it goes a little bit like with the hammer, because one has to think about total differentials. So you may want to look at that or not. It's actually interesting because it relates covariances and difference quotients, so that's interesting, so one gets a little bit more of a feeling of how the mathematics of these things work. But I don't think it's something that I really want to go over in all detail in the course. So the bottom line is, if you apply this formula that we now looked at here from an intuitive perspective, if you apply this in the context of a Gaussian random field with a 1D domain and a Gaussian autocorrelation function, you find that this measure of smoothness corresponds to the parameter of the Gaussian covariance function, which we have here. So that's this L parameter. And this is, of course, something that you are kind of familiar with. So if you think about computing the variance of a Gaussian distribution, you know that you get the variance parameter or the covariance function. But this is always something that, of course, in the last term we also discussed, you should not confuse. You can, of course, compute the variance of any random variable, and sometimes and often you might not then get just a single parameter, but a combination of parameters that give you the smoothness if you're in a parameterized domain, or you compute, you estimate a variance from something where you don't even have a model, like you compute the standard deviation or a variance from some observed data, like you did in undergrad statistics. And the same thing applies here. So this measure of smoothness that is there, you can apply that to any random field. But I state that if you apply it to a Gaussian random field with a Gaussian covariance function, you actually recover then I would call it the smoothness parameter of the Gaussian random field. Good. So I stop here, and I will tell you something about next and the week after in a second. So I'll just stop. Any questions? Yeah.
You just said that in SPM you get 3 sigma values, right?
You actually know you don't get sigma values, you get full width, half maxima. We will discuss that in detail.
We discuss it next.
We have to.
No.
Yeah, maybe that's the last point. So in the SPM, I can actually show you that because it's right here. Or is it? No, not in my. It's there. In the SPM table that you get in the end, you see this measure of smoothness, but it's called differently and it's parameterized differently, but it's there. Okay, with that, let's stop.